Greetings, math friends. I want to talk about a theorem about a continuous function that shows that its domain and its range are both closed intervals. But before we get to that, we need to take a look at this lemma, which is like a miniature theorem that helps us prove another theorem. It also requires a proof of its own to be thorough and rigorous. This lemma says that if you have a function that's defined between a set we call the domain and a set we call the range that is continuous, and that we also know that D is compact. This is a special situation in mathematics, so it's describing something about this set. Then we can say that there exists two elements of this compact set, which is our domain, where every other x that we choose in that domain is going to fall between the images of these two that we have chosen and the image of any of these values that we choose. In other words, if we choose two different values from this domain and we put those through the function, that will map into some number in the range. So this is a number and this is a number, which are defined by putting these numbers into this function. Then we can choose any other number that we want from this domain and put it through the function, and those values will all fall between these. Essentially, this is the smallest number in our range. This is the largest number in our range. So any number that we choose either has to be between them, or we've re-chosen one of the ones that we've already chosen. That's where you get the equality from. So if this was like a random draw, and I just, any number in that domain, I pick it out, I run it through the function, it's either going to be between, or it's going to be, I've chosen already one of these numbers, which we've distinctly said that we already had. That's where the equality comes from. So like if this was the number 1, we put it through the function, it gives us 5, so that 5 would be the smallest value there. Any number we randomly choose now should give us a number that's 1 or larger. In Galgan's book, Introduction to Analysis, he has this quote in the book, and I liked it, and I wanted to kind of repeat that or have that expressed for the video. The E and the R are taking the place of the D and the R here, so there's just a E substituted for D here. Galgan says that if the function from E to R is continuous with E compact, then not only is the function a bounded function, but the function actually assumes a maximum and minimum value on the set E, which is kind of what we just discussed here. This was a quote from his book that was published in 2009. It was the 5th edition of that book. I'm not sure if this same quote appears in earlier editions or not. Now that we've talked about this little lemma to help us prove the theorem, I want to talk about this other theorem that I'd really like to prove, which I just think is an interesting theorem that comes out of introductory real analysis. So this is the theorem that I really want to prove here, and I just think it's an interesting theorem. It says that if we have this function, it's a continuous function over this interval, which is going to be our domain, then we know that its range is going to be of this form, which they're both closed intervals. And then further, you can conclude that this value is going to be the minimum of all the function values when we look at all the values in A to B, and then M is going to be the maximum, which is kind of what we just discussed in the discussion of the lemma. So the first thing that we do as we talk about the proof is we kind of want to talk about some of the things that we have that we take as givens. So basically everything before the comma where we say the then statement, we can take as things that we can know and use. So we're going to start out with let f be a continuous function on AB. Right, so we've just taken that statement right there and just rewrote it as, we're going to start out with this. So we have a function named f. We know that it's continuous, and we have this interval AB, and this is going to map to here. This is part of what we want to conclude. All right, next we're gonna say that we can take two elements out of this because this is not empty. That could be a statement we can more furtherly say explicitly that this interval is not empty. All right, just like in our lemma, we're going to declare some x values coming out of the interval that we have. So that's just saying that I've got, this is the first x that I pull out, this is the second x that I pull out from the interval AB. It doesn't matter what these letters actually are. You could have called these y's, you could have called them z's, you could have called them a's and b's. We're just following a bit of the form of the lemma, though. So this is an x value and an x value, which is very traditional to say that your x is your independent variable. And then a and b are just your endpoints of your interval. We're further going to say that these images are as stated in the lemma. So f of x sub 1 must be less than or equal to f of x, which must be less than or equal to f of x sub 2. Right? So just like we had in the lemma. We know this is true from the lemma. Now that we know that there are values we can pull out of this, which gives us the images of these values versus any other element that we pull out of here that aren't the endpoints, we're just going to go ahead and name these values. Typically, these would be y values in like an Algebra 1 course. If you're in a higher level math class, we call this the image of these input values. But we're just going to name them with a single symbol. So go ahead and say let... we're going to use these right here. N equal f of x sub 1 and m equal f of x sub 2. All right, so we're just naming these two one symbol each, which happens to be the symbols where we are trying to get to. Now we're going to call in another theorem that I haven't mentioned yet, but is really famous. We're going to talk about the intermediate value theorem. So by the intermediate value theorem, if we have this lower value, we have some other image, and we have this, then we can conclude that y is going to be equal to some f of x here in the center, where x is from this interval here that we're talking about. So now what you see is we can substitute, we have this substitution right here. The f of x that we were talking about here is the y, the f of x sub 1 is the n, and the f of x sub 2 is the m. But if that is the case, if this is the smallest value this is the largest value and every other value falls in between. Well, this then is defining the range of the function f. So the function for any value from this that we plug in is going to give us any value from this range. All right, so the range of f is this, and we know that n is the minimum and m is the maximum value. So with that, we could conclude QED, or however you like to end your proofs. Pretty short proof, considering that we can call in the lemma that we had talked about before, and also the intermediate value theorem. And if you really go down the rabbit hole, the intermediate value theorem is supported by other theorems itself. Hopefully you find some interesting mathematics to share with others in your region of the world. Cheerful Calculations.